longest increasing subsequence. Sorry, I was contracted. Uh, kind of. So, subsequence of a given sequence is a sequence that can be derived from a given sequence by deleting some or no element without changing the order of the remaining element. For example, the sequence ABD is a subsequence of ABCDEF if we remove CEF. All right, it was quite simple, right? So if the given input string is are integers, then the longest increasing subsequence is uh, yeah is what is called is to find the longest increasing subsequence of the given sequence of distinct integers. So please note that there's a distinct, so there's no case of equal in our cases. In our case, so how to do it in an log n fashion. So let's d- just run it in this input string 9253 etc. Okay, so we fill this input string into this tabular form 9253 7 11 8 10 13 13 6. Okay, this is our input. This is our input string. So if we indexed this input string starting from 1, I mean the first position is 9, second position is 2, third position 5, fourth position 3, fifth position is 7, etc. Okay, so what we want to do is that we rate one character at a time and iterate over all the input characters. Okay, so if we read the input character 9, then we know the subsequence of length 1 we will have a 9. Okay, itself is a subsequence of length 1, and of course it is by definition an increasing subsequence. So we will in the following slides we will co annotate increasing subsequence as IS. I know that there may be some ambiguity. Just use this one. Quite simple, right? So the increasing subsequence of length 1 is also 9. So we have already read 9, and next we read 2. Okay, the second position is 2. Okay, so the increasing subsequence of length 1 is 9 and 2. Okay, so how do we find the increasing subsequence of length 2? Basically, we will try to append or add the 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 latest late the newly read character into the increasing subsequence of 1. Okay, if if the newly read character is larger than the end element, what is the end element? Means the last element of these subsequences. Okay, if the newly read character is larger than for each subsequence, for each increasing subsequence of length 1, if the end element of the the increasing subsequence is smaller than the newly read character, then we can expand it to a larger one. So let's say, so we just read 2, okay, but the only length increasing subsequence of length 1 at that time was 9, alright, but 9 is larger than 2, so 9 2 is decreasing, so we cannot form increasing subsequence of length 2. Okay. Next we we read the third position, which is 5, and of course, without any examination, we can add 5 into the increasing subsequences, the set of increasing subsequences, which is 9 2 5. Okay, so it is possible to form increasing subsequence of length 2. So we try to add 5, the newly read character, into the increasing subsequence and see if it works. So 9 5 is decreasing, so doesn't work. So 2 5 is increasing, it's increasing, so it works. So 2 5, so 5 is larger than 2, so we just concatenate 5 to the end of 2, so we get a new increasing subsequence of 2 5. And routinely we can read new characters one by one and do the same thing. Okay, let's say read the fourth position, and which is 3, and just add it to the increase subsequence and try to append. Okay, 9 3 is not increasing, 2 3 is increasing. Okay, 5 3 is not increasing, so we add 2 3 to the increasing subsequence of then 2. Okay, so what we have found is that we don't need to store so many things. The only possible way of extending increasing subsequence to the next length, I mean from length 1 to length 2 and from length 2 to length 3, is to is to append the newly read element to these subsequence, but we only need to memorize or store the subsequence. For each length, we only need to store the subsequence with the smallest end element. For example, in this one, 9 2 5, we only need to memorize or store 2, because if 2 is the smallest among 9 and 5. So if we read 3, we only need to compare 2 and 3 to see if it expand to us increasing subsequence. If that's 2. Okay. So for each for it for in sequence subsequence 1, before we store all the possible possible increasing subsequences, and so just the case for length 2. So after the observation, we only need to store this increasing subsequence with the smallest end element. Again, end element mean the last element of the increasing subsequence. So 3 is smaller than 5, so we only need to store this one. Okay, so it kind of reduced can reduce the work we need to do. So we again read the fifth position, which is 7. 7 is larger than 2, so we can add 2 7, but 2 7 is a increase subsequence of length 2, but it is not. But but the end element, which is 7, is larger than 2 3, so we just ignore or drop 2 7. Again, 7, if we want to generate or to form, to create length increasing subsequence of length 3, we try to add 7 to the end of increasing is of length 2. So 2 3 7. Okay, this newly formed in is of length 3. Okay, so we have 7 2 2 2 3 2 3 7. Again, the sixth position, which is 11. Again, 11. Add we can form 2 11, but again it is larger than 2 3, so we drop it. 2 3 11, but which is larger than 2 3 7. I mean larger meaning if we compare to subsequence, the larger mean the comparison between the end element, like 2 3 11. The 11 is larger than 2 3 7, which is the end element is 7. Okay, so we just drop it. But okay, of course. Okay. So again, 2 3 8 is larger than 2 3 7, so drop it. 2 3 7 8. Okay, a newly formed increases subsequence of length 2. So 2 3 7 8. So still a lot of works. So we want to know what can be skipped or neglected. So let's observe what's the observation. Once we read a character in, we will compare the newly read character with each end element for each length, right? 10 is larger than 2, but if we form 2 10 is smaller than 2 3, and 10, okay. So it is a good go, but it's not the smallest end element of length 2. Again, 2 3 10 is increased subsequence of length 3, but it is not the not the one with the smallest end element. The smallest end element is 7. Okay, and 2 3 7 10 is again, of course, it is an increasing subsequence, but it is not the not not the smallest one. The smallest one is 2 3 7 8. So we drop it, and lastly, at last, 2 3 7 8 plus 10 is 2 3 7 8 10. Of course, it is a newly formed in IS of length 5. Okay. So, what else can be forfeited? I mean, can be dropped or be reduced. So we the thing is the so from this we compare the end element and the newly read character one by one from length 1, length 2, length 3, length 4. But we can observe that in the first three cases, all the newly formed in increasing subsequences were dropped because they're a smaller one in the current state, right? So the properties is that the end element of these increasing subsequence is increasing. I mean, the end element is 2. The end element is 3 for length 2. The end element for is of length 3 is 7. The end element of is of length 4 is 8. And finally, the end element of is of length 5 is 10. So with respect to length, I mean 1, 2, 3, 4, 5, it is increasing 2, 3, 7, 8, and 10. So once we read a new integer or new character, but in this case it is of course an integer. Okay, we want to before we compare it one by one to length 1 to length 2 to the end element of length 1 length 2, meaning comparing 13 with 2, 3, 7, 8, 10. Okay, so we have to compare it 5 times. But do we have to? No. In fact, by comparing the newly read died, God's sake, for comparing newly read data integer, there are only 3 cases. Should not say condition. This case 1, case 2. The first one is the newly read integer is larger than all these end elements. The second condition or second case is that the newly read element is smaller than all the end elements. Okay. And the third is that the newly read element x resides in between two of the end elements. For example, if the next element is 99, so 99 is of course we can larger than 0, 3, 2, 3, 7, 8, 10. So we can just append it to the end, okay, to form a newly increasing subsequence. The second case is it is smaller than all these end elements. So if, for example, x equals to 1, so we just update the end element from 2 of is1, I mean is of length 1 to 1. Okay. The third case, Kx resides in between two of the end elements. Let's say 5, x equals to 5. I mean the newly read integer is 5. So we just update because 235 is smaller than 237, so we just update increase the subsequence of length 3 to 235. Okay. For this case, 13 is the first scenario, which is it is larger than all these n elements. So just append it to the end, so to form a larger or longer increasing subsequence. So the point is, after reading an integer x, we want to find the smallest and element out of all the current 6 and elements at this time. Okay, that is larger than x. Okay, what do you mean? What does it mean? If we read 6, this one, we want to find the smallest and element that is larger than 6. So among all these 6 and elements, 7, 8, 10, 13 are larger than 6, right? But the smallest element and element that is larger than 6 is 7, right? Which means the increasing subsequence we want to update is of length 3. So we can update 237 to 236 by concatenating 6 to the increased subsequence of length 2. Okay. Concat 6 to length 2 to 3, so 236. And again, we can see from like this one, 3 can trace back to 2. 6 was concatenated to the end of 3, right? 2, 3, 7, 2, 3, 6. Sorry. So for length 2, length 4, it is 2, 3, 7, 8. So 2, 3, 7, 8. Okay, 2, 3, 7, 8. It is subsequence because the order was not changed. For length 5 is 2, 3, 7, 8, 10. 2, 3, 7, 8, 10. For length 6 is 10. 2, 3, 7, 8, 10, 13. So, in fact, we do not have to store all these sequences. We only need to store, what we only need to store is first the end element. It is what we compare. It is by which we compare with the newly read character, newly read integer, right? And second is that what is the previous position in this case, right? If we want to know after reading all these integers, we want to know what it is the longest increasing subsequence of length 5. So we can, okay, I know the n element is 10, but I don't know. If we only store the n element, we can never know what is the complete form. So we need to store for each position the previous position in the longest increasing subsequence. Okay. So quite simple, right? So we we can declare an element which store the AND element for the longest increase subsequence. So AND element K stores the index of the AND element of increasing subsequence of length K. Okay. Sorry. Longest increasing subsequence. Okay. And previous index is just this arrow we drew in the previous slide. All right. The previous element in the increasing subsequence. And of course, an element is equal to an index. Just want to show the an element. So, like the element is 7, index 1. So it is all implementing this. And you only need to either choose to remember the index or remember the input input element. Okay, so let's say sorry. Okay, this is the case Professor raised, and the class which is 74920 12 2 3 15 6. Okay, so 749 12 2 3 15 6. Okay, let's start. Also, we read 7. The first index is 7, so we just append it. Okay, so the AND element of increasing subsequence of length 1 is 7, of course. So the corresponding index is 1. Okay, quite simple. The previous index is pointing to itself, so it's also 1. So after we read the second position, which is 4, we want to find again the smallest AND element of that is larger than the newly input. If you forget why we do this, you can go back to this slide. And by comparing it, I mean I forgot to say that to find the smallest AND element that is larger than x. Since the AND element is increasing, so we can, for a given newly read integer, we can locate its position or find the smallest AND element in log n time because it is a sorted increasing sequence, so we can use binary search. So this is log n. Okay. So the input is 4. What is the smallest AND element that is larger than 4? It's of course 7, right? So this is the first case that it is smaller than all of the current AND element. So we just replace 7 with 4. Okay. And don't forget to store the previous index to itself. It is because it is start a new possible increases subsequence. So it is starting from 4, which is pointed which should point it to itself. So the previous location should also be 2. Okay. So condition 2 is smaller than, then all these AND elements, so replace the increased subsequence of length 1. So we continuously read the third position, which is 9. What is the smallest AND element that is larger than 9? So let's know. Let's know. So it is an empty set. What should we do? Okay, this is the first case. The newly read is larger than all these AND elements. So we just append it to form a longer increased subsequence. So we just append it to AND element. Okay, append 9. And of course, the corresponding index is 3, right? The previous index is 2 because it was concatenated to the increased subsequence of length 1, which is 4. Okay, then the position is 2, so the index is 2. And again, we read the fourth position, which is 12. What is the smallest AND element that is larger than 12? Again, there's none, so empty set. We just append that 12 to the element, 4 to the index, 3, meaning that it should be concatenated to the length of to the increased subsequence of length 2. In this case, which is 9. Okay, so we know the current is 4, 9, 12. Okay, we read 2. What is the increased subsequence that what is the smallest AND element smallest AND element that is larger than 2? So 4, 9, 12. All of these AND elements are larger. So we just update the first one 2 by 2 and 5. And since it's a newly formed, it should point it to itself, which is 5. Alright, so the previous one is 5. So after we read the sixth position, which is 3, what is the smallest AND element that is larger than 3? So 2, 9, 12. 2 is smaller than 3. 9 is larger. 12 is large. Here we compare it in hand. Of course, in program we should implement it by binary search. So of course it is 9. So we replace 9 sorry, with 3, meaning that we have a increase some sequence of length 2, which has the smaller and element. So so we can append 3 to length 1, which is 2. So 2, 3. So the previous position should be 5. Why? Because the length 1 is 2 currently. Okay. 2 and its position is 5. So we say 5. So again, okay, notice that the previous index is just how the increased subsequence was formed. Okay, 2, 3. Okay, so going now, we can finish up. Okay, just forgive me. This is quite excruciating after you got COVID. I mean, if it's a serious syndrome, for God's sake. Okay. So, in program, we only need to keep 2 array. The first one is previous index. The second one is the end element or end index. Okay, so we can you can try the code here. So let, let's just write this one. Okay. So learn and nums is the input sequence. So first we declare, but I remember. Okay. Okay. In the code, it does not require to return the longest subsequence. It only need to return the longest the length of the longest increasing subsequence. So it's much it's much simpler because we do not need to remember the previous index. We only need to remember to store the end element. Okay. So can declare a vector of integer coded end element and the case okay. And next, what we do is iterate one by one. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and 7. Okay. What should we call the newly read integer? Okay, we just call it x. Okay, to be consistent. So what should we do after we read an integer? We compare it with the end element. How to compare? Here, we can show you the lower bound. Okay. Okay. This is a standard a standard standard STD library. So losing my voice. So you can uh, see it more clearly in the standard library. Uh, does not compare less than value, which is does not compare. Not less meaning larger, right? Not less. Sorry, to forget how to write C++. Ah, got it. Hmm. Mm. Okay. Okay. So the return value is an iterator. Okay. Okay. The first element. The second element. The last. The value is x. Okay. If eta What does it mean? It means that it is larger than all these elements, which is our case. Case what? Case 1. We just append it, right? Okay, right? We just appended 99. We appended. Okay. Another case. it if it so in our case there are case 3, 2 and case 3. So we in both these cases we can find 2, and of course in this case it's 5 because 7, right? Because 5 resides in between 3 and 7, so it is 7 we want to replace. And in this case it is 2 we want to replace, so we always can find an element, so we just replace it. If we want to render or produce the trace backend in as the slide state, there will be 3 cases, but in the code we only need to return the dance, so it's only 2 cases. So uh so uh time complexity should be log n because you can use binary search. Okay. So in finding this one, it's messy. Ah. Okay. So the total time complexity for each input integer is log n. Okay. So the time complexity should will become n log n, right? I mean, length length Okay. And after iterating all these, we only need to return the longest one, which is the last one, right? Sorry. Okay. Sorry. And it is, of course, integer. What? Alright, alright. Where? Oh, for God's sake. This one. Wow. Keep overflow. Okay. Oh. Okay. Oh, can use back. Sorry. Yeah. 14. Output 14. And element. Okay, it's an element. We want to store return the length. Okay, the length. Okay. So okay. Is a okay faster than 74%. Memory usage less than 70%. Okay, not too bad. So if you understand Mandarin, there's a programmer which really explained it really well, much better than me. And he also mentioned the relation between the patient sorting of this case. So we can I will put his YouTube link in under in the comment. Okay, let's finish here.